All right, so welcome back. So now we're looking at one more example here with absolute conditional convergence, and it is the sum, series as k goes from 1 to infinity, of sine k over k squared. So this is no longer even an alternating series, right? Depending on the values you're picking here, sometimes the terms are going to be positive, sometimes they're going to be negative. All right, so we're looking at sine k over k. So the first term, sine 1 over 1, is 0.84. The next term would be sine 2 divided by 4. It's 0.22. The next term would be sine 3 divided by 3 squared. Also positive. But now, the fourth term, sine 4 divided by 16, right, that's negative, as is sine of 5 divided by 25. That's going to be negative. And sine of 6 divided by 36. That's going to be negative until we get to sine of 7 divided by 49. Right, we're back to positive again. And we'll stay positive for a little while. And then we'll have a few terms where it's negative. And it'll keep doing that. So it's not an alternating series. And it won't always maintain that three positive and then 3 negative. Sometimes, depending on where you get to, you're going to have maybe 4 positive in a row or 4 negative in a row. But it will keep swapping back and forth between that. And we're adding all those terms up. So this is not a alternating series. This is just a series where the terms are sometimes positive, sometimes negative. And we're still adding them up. So we're going to look at absolute convergence first. Sum of the absolute values of the AK. So that would be the series. K goes from 1 to infinity of the absolute value of sine k over k squared. So we start to look at that. And so you might suspect, oh, I'd like to compare that to the p series 1 over k squared. Right? That's reasonable because sine k, absolute value of sine k, is always just going to produce numbers between 0 and 1. So why not just compare this to 1 over k squared? So we know that 1 over k squared, we know that is a convergent series. So try to use our limit comparison test, in other words. Try to use our limit comparison test. Because I certainly don't want to try and integrate absolute value of sine k over k squared. That doesn't sound like a good thing. Okay, so we use our limit comparison test. Limit as k goes to infinity of the first sequence, absolute value of sine k, over k squared, over 1 over k squared. And simplify, the 1 over k squareds go away. And limit as k goes to infinity of absolute value of sine of k. Unfortunately, sine never settles into anything. That limit does not exist. And we're like, oh gosh, what do I have to do now? What do I have to do now? Right? What do I have to do now? Right? Because 1 over k squared didn't work. 1 over k squared didn't work. Remember what the limit comparison test tells us. Right? The limit comparison test tells us that when we're comparing the two limits, if the limit goes to 0 and the denominator converges, then we can say that the numerator will converge. If the limit goes to some number and the denominator converges, then we'll be able to say our thing converges. If the limit goes to infinity and the bottom diverges, then we can say it diverges. Okay, but we're not getting any one of these. We're not getting any one of these here. We're not getting any one of these here because those k-squareds completely dropped out and it left us stuck with the stupid sign. Now, if I had had a limit that involved this sine thing divided by something, then I could say, well, I don't know what sine's going to go to, but it's always between 0 and 1. And if I had a denominator, like if I had sine k over k, then I could say, well, k goes to infinity, then that's going to be a number between 0 and 1 over infinity. I could conclude it goes to 0, but the fact that the k-squareds canceled out, that created a little bit of a problem. But if we just go down to something smaller, a little bit smaller than k-squared, power-wise, that still converges, then we'll be okay. And so here the trick with the limit comparison test is let's compare this to something like 1 over k to the 3/2. Okay, that also is a convergent series. P series is greater than 1, so that's going to converge. And then this fixes our problem. So sometimes you just have to be a little careful in the selection of the series you're going to compare it to with that comparison test. We actually saw a similar thing with the ln that we ran into when we were comparing it, ln of k over k. Similar idea where we actually had to pick this guy. Okay, so what's going to happen here is that k to the 3/2 is going to come up and it'll cancel with the k-squared. That'll give us limit as k goes to infinity of absolute value sine k over k to the 1/2, or square root of k. And as k goes to infinity, k to the 1/2 is going to go to infinity. Sine k is going to keep alternating between values, following his smooth little thing, but it's always going to be a number between 0 and 1. So when you take a number between 0 and 1 divided by infinity, that's going to go to 0. And since this limit goes to 0 of this fraction, and we know the sum of the 1 over k to the 3/2 converges, right? The bottom sequence converges. We have a limit going to 0. So we do know that the top sequence is going to converge. So the original sequence we were looking at there, absolute value of sine k over k-squared, that thing is going to converge. And so since the absolute value converges, we know that the other sequence, when we drop the absolute value, will also converge. So we say that it converges absolutely. This sequence here converges absolutely.